And now we're all set. So you can start. Please go ahead.
Um, Hello. So I'm gonna talk to everyone about the role of superfluidity in nuclear fission. And this is a rough outline of the talk. There'll be some background in what is nuclear fission from the theory point of view, the framework that will be applied, which is density functional theory, and its extension to superfluid systems. Um, the first application of a microscopic framework to real-time fission dynamics. And then after point three is when I joined the group at the University of Washington and some of the specific work that I've done. So some historical context, fission was discovered in 1938 by Hahn and Strassmann. Um, Just a few months later, it was explained by Lisa Meitner and Otto Fritz. And I'm going to draw your attention to this plot here, um, because I think their explanation is very intuitive. It's not microscopic, but it gets into the heart of what causes nuclear fission. So, as you might know, fission is when you have some compound nucleus that eventually splits into two or sometimes more fragments. And in this process, releases a large amount of energy, both in the kinetic energy of the remaining fragments and in the fact that they're hot nuclei. So they have excitation energy and can emit neutrons and gammas. So their explanation is basically think of the nucleus as a charged liquid drop. Um, which is not so bad because we know the nucleus is roughly an incompressible fluid. So what happens if I take a charged liquid drop and I start to stretch it? Well, the Coulomb repulsion, the Coulomb energy is going to go down because the protons in your system are getting further apart. So if you guys can see my mouse, you'll have a line going down, which is the contribution of the Coulomb term to the total energy. Um, and the surface tension, because the volume is going to be preserved, is going to go up because you're getting away from a more spherical object to a more elongated object. And this dashed line here is the result of the competition between Coulomb and surface tension. And so what you'll see is if you're on the left of this dashed line, you're a bound system, except for the possibility of tunneling, but that's not considered in the liquid drop model. But once you go past this point, known as the saddle point, then it's going to be energetically favorable for you to keep deforming. So this is just a deformation parameter, says how stretched your system is, until eventually you reach the point where the nucleus has to break into two. There's a little bit more to the picture. This is something known as a potential energy surface. Potential energy is a function of deformation. Um, in 1960, in the 1950s, Strudinsky highlighted that actually you have a metastable state due to quantum mechanical shell effects at finite deformations. And I'll show you the actual picture is slightly more involved in this as well. All right, so a bit of a more detailed overview of fission. So this is a very simplified, intuitive picture. Um, you can think of fission in terms of all of the different subparts of the process. And the thing that really makes fission a nice quantum many-body problem to tackle is its incredible complexity. And why is it complex? One of the big reasons is it has many different qualitatively distinct stages whose timescales vary by orders of magnitude, many orders of magnitude. So you can imagine trying to find some theory that can model the whole thing start to finish is going to be a very, very difficult task. And in fact, no one in the community is close to having a unified theory. But just to briefly explain some of the stages, these are very involved plots, but I'll bring your attention to the top one. You have the entrance channel, typically fission. You'll have a neutron be absorbed by some nucleus. It'll start to deform. It will split into two fragments. Those fragments will emit neutrons first, emit gammas first, and then much later, they'll beta decay. The part that's highlighted by the circle, which is defined by the potential energy surface I showed above, and here's a bit more details. This is the fastest part of the fission process. You can see it happens at the scale of 10 to the minus 22 seconds. And for a comparison, you're going to see the emission of neutrons start at 10 to the minus 18 seconds. So 4 orders of magnitude separation. This part is disputed by our group due to microscopic evidence, which actually is in the title slide. We see neutrons be emitted during the neck rupture phase of fission, but I don't have time to discuss that. So we'll leave that out and say that this is currently the leading assumption in the field. And you can see gammas will take, I mean, here's, I don't know, that's 19 orders of magnitude separation between the fastest phase and the emission of the last gamma. So this makes it a very difficult problem. All microscopic models right now focus on the first part of the fission process, this evolution from a compact shape to the formation of 2 fission fragments. Why is that? It's because we believe that the later stages can be reasonably well handled by statistical theories. But this part of the fission process is highly non-equilibrium. So you really need a real-time framework to watch the evolution. So now I'll talk about density functional theory, which is the framework we employ. And just some motivation. Many-body quantum mechanics is very difficult. And to give some context, imagine doing uranium-236, which is a typical fissioning nucleus, and putting it on a modest lattice, so 30 by 30 by 60 points. This is what we'll actually do in fission calculations. How many complex numbers would you need to represent the many-body wave function? If you ignore spin and isospin, you take the lattice raised to the number of particles, and you get an enormous number. So you know you cannot treat the problem directly. So one possibility, and specifically for fission, this is really the only thing people do right now, and that is density functional theory. So for the people who haven't heard of density functional theory, the idea originates from the Hohenberg-Kohn theorem in 1964. And it basically says there's a one-to-one map between this immensely complicated object, the many-body wave function, and the one-body density, which is the many-body wave function where you integrate out all degrees of freedom but one. And what this means is the one-body density can just be defined by the number of points in your lattice. So it's a very small object. In reality, you need more than just the number density. If you want to include superfluidity, you need the anomalous density as well. If you want to include spin orbit, you need a spin density, etc. But it's always going to be some maybe 10 times the size of this number, still a very small object. And this theorem is an exact mathematical theorem. You can prove it fairly easy for ground states. Um, what people realized is, okay, it's nice to have this relationship between the many body wave function and the one body density, but how do we actually, there is no easy equation you can solve for the one body density. So how do we get it? And this is the second paper in the series. There was a concept introduced known as cone-sham DFT, where the major idea is if you treat your many body wave function as a Slater determinant, which is what's a Slater determinant? It's just a product of you basically take your many body wave function and you treat all of the coordinates as individual orbitals, and then you construct a product wave function. And then because you're looking at fermions, you have to anti-symmetrize it. And this is the simplest thing you can do. Then in this case, you can actually, through a self-consistent procedure, solve what's known as the cone-sham equations and get the ground state density. Um, so you go from a picture of many particles which are interacting to a mean field picture, where now you have individual orbitals that instead of interacting in some static external field, interact in some mean field that's generated from all of the rest of the particles in the system. Um, Now let's talk about DFT for nuclei. Um, so what I described above, I mean previously in this slide, the simplest implementation is Hartree-Fock theory, where you'll get your orbitals, which will define your energy levels. You'll fill your energy levels up to the Fermi level completely. And this is Hartree-Fock theory, which will account for all of the long-range correlations in your theory. In order to have superfluidity, you have to extend Hartree-Fock to Hartree-Fock-Bugler-Above theory, where now at the Fermi level, you have a diffuseness of the occupation probabilities. So you basically go from single particles to quasi-particle orbitals, which are linear combination of particle-hole excitations on a Hartree-Fock vacuum. And instead of a Slater determinant, you have what's known as a generalized Slater determinant, which if you want some intuition for what this object looks like, it looks like a BCS wave function if you do H of B theory in the canonical representation. This is a lot of formalism. As far as the practical day-to-day, what's done is you'll typically start with a nuclear energy density functional. This is very similar to a Lagrangian, for example, if you were doing quantum field theory. You would minimize it with respect to your quasi-particle states. And you get some H of B equations. It looks like a Schrodinger equation almost. I mean, you have a Hamiltonian and then a four-component wave function, so spin, and then to account for pairing, and then some energy, some quasi-particle energy. The self-consistency comes from the fact that, okay, you have this Hamiltonian, you diagonalize it to get a new set of quasi-particle wave functions, use those to build a set of densities, and then you insert those densities back to define a new Hamiltonian. And you adjust the chemical potential at each step until eventually you get the correct number of particles and your results have converged, namely the quasi-particle energies or the densities or whatever you want to look at doesn't change from iteration to iteration. And if you want to do time-dependent DFT, which is our interest, then you promote the quasi-particle energy to an operator, so a time derivative. All right, so now to actually get into the meat of this talk, we're going to talk about the induced fission of plutonium-240 within a real time framework. This was a little bit before I joined the group at the University of Washington, but this is really where this entire enterprise got kicked off. So I said potential energy surfaces in reality are more complicated. So let me explain these plots here. The top panel and bottom panel are basically the same. The only difference is you're using a different energy density functional, so different starting assumption of how the nuclear interaction looks like. The x-axis is your quadrupole deformation. This is how stretched out your nucleus is. In reality, it's how football shaped your nucleus is. Or if you get to negative values, then how much like a pancake it looks like. And on the y-axis, you have octupole deformations. This is how pear-shaped your nucleus is. So if you cut the nucleus in half, basically how many particles are in the left and how many particles are in the right. And this deformation is very important because we know the most dominant fission modes is not you have a nucleus and it splits into two equal nuclei, two nuclei with the same mass. It typically splits into asymmetric nuclei. So one will be a lot heavier than the other one. And you can see this here. So to now explain what the points are, these are points with energy at the saddle point, going all the way back. This is the saddle point, the point of no return. You put a lot of trajectories at equal energy, and all of these you would expect to fission because it becomes energetically favorable to do so. And what you see is, okay, in some rare cases, you go symmetric, you have no mass asymmetry, no octupole deformation, but by far the dominant mode is the mass asymmetric mode. So this is going from the point of no return, known as and I'll just call it the saddle point from now on, up until when you form two fragments that now accelerate independently. So this is already the strongest evidence that superfluidity is absolutely essential for fission. In 2016, people used time-dependent Hartree-Fock theory, so no superfluidity. They started with points here at the saddle point, and they could only achieve fission if you include 200 MeV of excitation energy on top of those initial configurations. For context, realistic fission should be achievable with thermal nuclei, which are just a few EV of excitation energy. So you can see this is a big discrepancy. In 2016, in the same year, it was demonstrated that if you do Hartree-Fock-Buchla-Above theory instead, now you can fission with thermal nuclei. You don't have to include an experimentally unrealistic amount of excitation energy. And this was really the big achievement that showed, okay, there's something about pairing correlations that causes this phenomena to be possible. And that's what we're going to talk about here. This is probably the most important slide in this talk because it gets to the heart of what's why treating the nucleus as a superfluid allows you to actually deform to the point of scission. And I'll bring you back to the paper by Hill and Wheeler that sketches out a very nice picture of what's going on. So what they say is, you know, the nucleus is an incompressible fluid. As a simplest approximation, let us treat the nucleus as a 3D infinite square wall, whose energy levels minus the factors of h bar and so forth are included here. So what happens to these energy levels as I start to deform my nucleus? Or in this picture, pull one of the walls of the well, elongate one of the walls of the well. Since it's an incompressible fluid, you know the volume has to be conserved. So if I elongate one direction, at least one of the other two has to shrink. And so I break, if you start with a square, you'll have a lot of degeneracy. You'll break that degeneracy as long as you stretch one of the sides. And some levels will go up and some levels will go down. At level crossings, so here, look at the top panel where you have a single particle level structure, and then as a function of deformation. At level crossing, due to pairing correlations, it becomes energetically favorable to jump a pair of nucleons instead of just one. And this makes it much easier for, as the system starts to deform, for you to keep the total energy of your system down. Say if you had no way to transition between levels, just by energy conservation, you'd see very quickly it would be impossible to deform your nucleus if you were stuck in this level, for example. And this picture shows basically what happens. So this is the key idea, is pairing allows you a very efficient way to repopulate your states as a function of deformation. And in fact, these transitions are enhanced by a Bose enhancement factor due to the presence of these pairs. And this is not just for fission. This will be a common trend where very often in nuclear physics, for static properties like binding energies, charge radii, pairing is important, but in many cases you can get away with neglecting it, and it'll just be a small percent correction. For dynamics, it's always very essential. All right. In this paper, another result that was talked about that I think is one of the big results in the field is what is the character of the evolution from saddle to scission. Here's just a one dimension, so basically projecting out the octupole degree of freedom and looking at the quadrupole, just different functionals, different nuclei. So what I want to pull your attention is what's plotted here, these lines, are the intrinsic energy of your system. So what does that mean? It means you take your total energy and you subtract out the collective kinetic energy. Prior to 2019, what people believed is all of your intrinsic excitation would fall in the potential energy surface. And basically all of your the full excitation energy of your system is collective kinetic energy. So to give you an analogy, they believe the nucleus going from saddle to scission was similar to somebody jumping off a cliff and then the gravitational potential energy being converted very cleanly to pure kinetic energy. What we know actually is it's equivalent to somebody jumping off a plane, and very quickly they'll hit a terminal velocity. And at that point, in this case, where the terminal velocity is a very small number, at that point, you don't actually keep increasing your velocity or your kinetic energy. You just start to heat up. And that's what's happening here. If you look at the difference between the potential energy and the intrinsic energy, it keeps increasing because the intrinsic energy is roughly a constant. So this difference can only be temperature. And this has a lot of consequences for what is the energy of the fission fragments. If you assume what's known as the adiabatic approximation, that it's all collective kinetic energy versus that the compound system heats up as it evolves towards fission. Um, so I think this will be the last topic I'll talk about. Um, and this is something I did during my PhD at Washington. That's in my opinion is quite interesting. Um, so something you may or may not be aware of is in DFT, you actually break a lot of symmetries that you know should be present by the structure of your Hamiltonian. So you know the nucleus should have good quantum numbers, should have good total angular momentum, linear momentum, parity, um, and particle number. Um, because we choose an oversimplified many-body wave function that misses a lot of important correlations, i.e. a Slater determinant or generalized Slater determinant, you end up losing a lot of the symmetries that you know should be respected. As an example, let's say if we wanted our wave function to be a momentum eigenstate, if you have a set of a product wave function, the only way you can get a momentum eigenstate is if all of your single particle states are eigenstates of the momentum operator, namely their plane waves. And what does that mean? It means that you'll have a system that's unbounded. And if you want to bound its system, then you have to abandon that quantum number. And so really the symmetries in DFT are broken as a matter of convenience because we choose to select collective effects. We believe collective effects are more important than preserving symmetries. And here I've listed a few of them. Superfluidity, for example, including that, means now you don't have good particle number. You have good average particle number, but your many-body wave function is not an eigenstate of the particle number operator. Um, and then what's done is those symmetries are typically restored after you've done the full simulation. You have some sort of final state. For example, in fission, two fission fragments emerging. There's a more technical thing you can do, which is you can restore the symmetry during the time evolution, and you should get a better wave function in this way. But this is a much more involved process. So in 2021, by restoring angular momentum, our group was able to extract the spin distribution of the fission fragments for two nuclei for the first time. It was the first time microscopically you could look at these objects. And let me go ahead and jump here. The most interesting story from this was, okay, you have two fission fragments. They have angular momentum vectors, and those vectors will have some angle between them. And that's what's plotted here. So at 0 degrees, they're parallel. At 180 degrees, it's anti-parallel. And at the middle here, close to where this line is, if you can see my mouse, this would be them being perpendicular. There were basically two theoretical predictions for what this should look like from us and from a competing group in Berkeley National Lab. And you can see the predictions are very drastically different. The blue line is from Berkeley, and then from Washington is all of these points. You can forget the details of what exactly this means. Um, and this has a very clear interpretation, which is we basically predict the fission fragment spins will be unrestricted. Um, and the prediction by Freya is that the fission fragment spins will always be perpendicular to the axis of fission. So you can think of this as what would be the distribution if you had two uncorrelated vectors in 2 dimensions versus 3 dimensions. Um, I will say when we achieved this first result, we used an approximation how we restored the symmetry because at the time the computers and our framework was not advanced enough to actually do the full restoration. At a later time, we were able to finally do the full projection, and the big advancement was that we realized we can go to the canonical representation to cut a lot of the states from our system. Um, so it's a bit of a technical detail, but this is actually our new prediction in the bottom left, which still looks different from the result from Freya, but is a bit more similar. It gets a bit closer. Um, what's shown in the right here is let me actually pull your attention to the bottom right plot. Um, this shows the probability of your angle being away from the fission axis. I mean, away from the fission axis. So if you're at 90 degrees, that means both of your vectors are perpendicular to the fission axis. And as you move away from that, that means that they point slightly out of the fission axis. So basically, our new prediction is okay, it's not unrestricted, two vectors unrestricted in 3D space, but it's also not two vectors exclusively always perpendicular to the fission axis, which is what you'd get if the distribution was exactly 90 degrees. It has a kind of wide spread. And what's the relationship with pairing? The relationship is basically you can view this as a measure of if pairs are broken when your nucleus splits into two fragments or not. So if you predict pairs are unbroken, then it's true you will only have your fission fragment angular momentum vectors will always be perpendicular to the fission axis. But if pairs are broken, and now you can have some projection along the fission axis for unpaired nucleon, then you get a picture that's more similar to what we have here. And so in some sense, this is a prediction that during fission, when your fragments split, you must break a certain amount of pairs. Um, so let me briefly touch upon this since I do have some time still, which is the fission of odd nuclei. This was something else that we did kind of more recently. So what this is, now we're looking at many systems, but it's the same picture I've been showing before. You can construct odd nuclei in HFB theory by basically taking one of your pairs. So let me go here to what the wave function, what a BCS wave function would look like. Where instead of creating a pair, in one instance, you just create a single particle. And let me, so basically we did this for many nuclei, and we also evolved trajectories where we treated them as even nuclei. Because it's a bit weird in DFT, you can have an average number of particles that's odd or even, but the character of the many-body wave function can still be even or can still be odd in both cases. Um, so to really see the effect of having one unpaired nucleon, we kept everything fixed except for the structure of the many-body wave function by doing a flip on one quasi-particle orbital. And probably I'll conclude with this result because it has a nice intuitive explanation. If you look at the plot here, what we did is for the exact same deformations, average particle numbers, the only thing is treating the system as odd, so one unpaired nucleon, or two in the case of Neptunium, um, versus treating it as even. We looked at the time it takes for the system to evolve from the saddle point to scission, the formation of two fission fragments. And we saw very systematically at low quasi-particle excitations, the odd system was slower. And this relates exactly back to the Hill and Wheeler picture. Now you have one nucleon that's unpaired. So it's not going to be as efficient in redistributing its occupation as the system deforms. We also noticed, so what this is basically zooming in on the potential energy surface and looking at the evolution for some range of octupole and quadrupole deformations. We noticed that the evolution is much more chaotic in odd systems. So you can see if I say starting from the left and going to the right, I follow this black line, it undergoes quite a lot of oscillations, the same with this red one and so forth. Um, so it seems like this also relates to why it takes longer for the system to actually eventually separate and reach scission. So this is interesting that when you have one unpaired nucleon, the evolution becomes so much more chaotic. Um, this is a bit of a technical point, but it's a comment in the commonly used Pauli approximation, which is, okay, you have one state. So if I construct the HFB wave function of this form, which if you have an odd nucleus, you can always bring it to this form. You, at your initial time, you always have one state that's occupied with probability one. In the Pauli approximation, the assumption is made that at all times that state is fully occupied. We started with this configuration. We just looked at the time evolution and looked at the occupation number, and we see very quickly it actually redistributes its occupation probability. So this means probably for time-dependent phenomena, this is not a reasonable approximation to make. Let me go ahead and conclude with a summary. So fission is a very old quantum many-body problem, over 70, 80 years now, a bit more than 80 years now. Even though we've made some recent advancements, we are very far away from having a full solution to this problem. And there's a very high likelihood we might never get there for some of the reasons discussed before. But still, I hope if you can take one thing away from this talk, it's the fact that pairing has been demonstrated to be very critical to modeling the saddle scission phase of fission. As in, if you neglect pairing, you're not going to be able to do it unless you make some very unrealistic physical assumptions, like too much excitation energy, or you start with way too deformed of a initial state, way beyond the saddle point. Yeah, thank you very much.
Thank you. This is really interesting. And so people in the audience, if you have questions, please put your hand up. Um, but before anybody else has the opportunity, I'm going to grab this and ask you possibly a slightly naive question.
Mhm.
Um, is it the case that this odd even difference in the timings that you just described is connected to the phenomenology of, say, the stability of odd versus even nuclei in some way?
Um, yes, it very well could be. It could be because you have much more low-lying states for odd nuclei that the picture that you're actually encountering, and let me go back to the potential energy surface, because this is just the lowest potential energy surface. But we know in practice, as soon as you're in this regime and you have some temperature, you have a lot of potential energy surfaces on top of that. Um, it could be for odd nuclei, you just have a much more dense structure of levels or potential energy surfaces that you can jump between that ends up confusing the system. And basically, you have a picture in the even case where you're just driving through a kind of smooth valley. And in the odd case, because of the structure, you're driving through a place with many obstacle courses. And that's what's causing the slower time. So it is very reasonable, yeah, to say that.
And then this general observation that there's a difference in the stability of odd and even nuclei has to do with the existence of this pairing in the first place. Is that, I mean, I'm just trying to remember some of the motivation I've seen for this kind of
I mean, the
field
stability
and
is
so on.
basically going to be determined by the gap between the state the um the state below the Fermi, the closest state below the Fermi surface, and the
Yeah,
closest state above the Fermi surface.
yeah,
And for odd nuclei, you have a smaller gap, and you have a lot more levels
yeah,
close to the Fermi surface above it as well.
yeah. All right, Mark, please.
Yes, thanks very much for a very interesting talk. It's all very new to me. And so I have a question about I want to get a better idea of sort of the computational complexity of the problem coming from an angle that I'm doing time-dependent Ginsburg-Landau simulations. But it sounds like you're doing that with the mean field, and you're also doing some solving Schrodinger equations for particle states as well. So how many fields are there distributed on your grid, and what determines the boundary of the nucleus, for example?
Um, yeah, so let me go back to this slide here.
Mm.
The number of densities, actually, all of them are listed here, where you'll notice some of them are vector quantities. And then the dimension of each of these is going to be the number, basically your
Mm.
lattice. And it depends on the problem you're looking at. So for fission, we found 30 by 30 by 60 with one Fermi spacing is good. If you want to do collisions at finite impact parameter, then you need a slightly larger lattice. For the computational complexity, um, this equation here, in a lattice, if you don't apply any cutoff, which is the case we do, um, is dimension 4 times your
Mm.
lattice by 4 times your lattice. So we're diagonalizing a 100,000 by 100,000 matrix. And time evolution looks very similar to that. In fact, all of these calculations can only really be performed in supercomputers due to their computational cost. And um, this one, which is a much bigger lattice, this is 120 by 48 by 48, which was a study we did specifically to look if there were any neutrons emitted as the nucleus ruptures. This took all of Summit, or you could say maybe 1/8, 1/4 of the resources of Frontier to do such a calculation. So it can scale very, very quickly.
Right. Yeah. And yeah, sorry, I missed that first slide. So what was being plotted there on those
Oh, yeah, sorry. I didn't go into detail, but this is on the profile of the neutron density
neutron
log
density? Yeah.
scale. It's a time series. So scission is when the neck basically starts to rupture a little bit before and then after. And what you see is when the nucleus splits, there's clouds of neutron density um, that are being projected in different directions. And this was why at some point in the talk, I said, even though it's commonly, I mean, the consensus from the community is you should probably see neutrons emitted from the fragments at much later time as a thermal process. We call that into question. And now I think a lot of people are thinking about this. I should say, I should be careful. Actually, this idea of neutrons being emitted at this stage goes back to Niels Bohr in the 1930s, a long time ago. But after a certain point, it seems to have been dismissed. It had some traction in the 50s, and now we're trying to suggest that maybe it shouldn't have been dismissed so easily.
Yes, I think Niels Bohr probably had quite good intuition, but yeah.
Yeah, no, it's definitely. It's a
Yes.
good place to be on if Niels Bohr suggested.
Yeah. Yes, thank you.
Yep, you're very welcome.
There was another question I wanted to ask you. This is kind of an experimentalist one. Would it be easy to estimate or somehow outline what the basic parameters of superfluidity would be in terms of order of magnitude, things like the pairing gap or coherence length or these kind of things?
So actually, this is a topic of big debate, which is what would be the best experimental observables to get at I mean the pairing gap is not necessarily going to be the most difficult because you can get it from the binding energy difference between odd and even nuclei. There'll be things like the 3-point and 5-point formula that people commonly use because this is where people discovered in nuclei that there should be pairing. They looked at the binding energy between even, binding energy between odd, saw staggering at the level of 2 MeV. And so you assume that in the odd systems, there's one unpaired nucleon, and that accounts for a slightly related question, which is can you use experiment to distinguish between the treatment of pairing correlations in these different theories? I believe yes. And in fact, we put in the archive or trying to get published recently a paper where we look at heavy ion collisions and specifically particle transfer under the barrier. And what you'll see is, and I'll go here to a slightly different framework. Where do I mention it? Maybe here. Okay, here. What you'll see is if you treat pairing as not a field in something known as the BCS approximation, which should not be confused with writing a full BCS wave function, which is what H of B would be. It's an approximation where you treat the pairing field with the correct magnitude. So the gap is the same as in H of B, but you treat it as a constant field instead of a field that depends in space and that can change as that can have fluctuations and local effects. You will not be able to experimentally describe particle transfer under the barrier. So even for a lot of easy static observables, such as binding energies, or you could look rotational states as well as another common one for nuclei. Even if two models can do the same predictions for static observables, it does not guarantee that for dynamic observables they'll lead to the same prediction. And so, yeah, I would say if you wanted some dynamical measurements of both the magnitude but also the treatment of pairing, then there's definitely things you can look at. You can look at particle transfer under the barrier for heavy ion collisions, for example. For fission, I'd have to think about it more outside of the fact that if you don't include fission in your theory, I mean, if you don't include pairing in your theory, you don't even get fission.
Yeah, that already answers the last question I was going to ask, which is what sort of an experiment should one design to probe kind of consequences other than the ones that you've already described. I don't see any other questions in the audience, so in that case, we'll just say that the next webinar will be in 2 weeks' time, given by actually Mark's collaborator, I believe, who and Lina as well, who will be talking about using time-dependent Ginzburg-Landau simulations to understand first-order phase transitions in superfluid helium-3. That's in 2 weeks' time. And then I would like to thank the speaker for another time. It was really interesting to follow this, and thank you for the presentation.
Yeah, thank you for inviting me.
Yes, thanks. And with that, I believe we're finished. The recording will appear on YouTube in some time.
Thank you, guys.
All right.
Bye.
Bye.
Thank you.